And let's welcome our fantastic keynote speaker, Mr. Les Johnson, well-known science fiction author, physicist, and NASA technologist, who will introduce us to A Traveler's Guide to the Stars. And for those of you who sits farther away, that's exactly the title of the book that is here, that was written by Les. The stage is yours.
Thank you very much. Yeah, good morning. I have the privilege today to share with you from a lifelong research into interstellar travel that began reading science fiction novels when I was about 8 years old. I ended up following a career in physics because of that and watching as a 7-year-old Neil Armstrong walk on the moon. I remember my parents waking me up in the middle of the night to see that, and I'm forever grateful that they did. But I have to emphasize I'm not here speaking as a representative of NASA today because I write books on the side, and it's not part of my official duties. So I'm here to share with you as a writer, a dreamer, a futurist, and someone who shares a common vision, I think, with most people here of our exploration, not just of the solar system, but eventually the universe. And so if you can bring up my slides, I'll go ahead and get started. One of the things that I get asked a lot is with the recent discovery of exoplanets, what about exoplanets? Can we go? And I mentioned I was a science fiction reader, and prior to the 1990s, we had no scientific evidence that there were planets beyond our solar system. I think planetary scientists and astronomers knew they would be there. The science concluded that we can't possibly be unique in the universe, but there was no data that said, there's one. And we've confirmed it. So the only place I could read about real exoplanets, in quotes, was in science fiction. And this is some of the science fiction I just loved, including the German language Perry Rhodan series, which has been in continuous publication since the year of my birth, I believe, and was translated into English for a while. There are more than 5,000 exoplanets known today. And when I say known and confirmed, to be confirmed, it has to be detected by more than one method, and that would be a whole lecture in and to itself. But taking this data point as a representative example and looking at the fraction of the universe in which, or our solar galaxy in which these exoplanets have been discovered, which is that little oval on the picture here, you can see that within just this small region of the galaxy, we have discovered lots and lots of potential places to visit. So the question comes back, how do we get there? Is it possible to go to the stars? Can we have the technologies in the future that enable this? Is it allowed within the laws of physics? So the talk I'll give today is firmly constrained in our current understanding of the way the universe works. I won't be talking about hypothetical physics, physics that is not real, or science fictional drives, although in my book, as a science fiction fan, I do have a chapter devoted to talking about those and whether or not some of these that we really love in science fiction films and TV series could ever become real based on our current understanding of the universe. So you can't write a book called A Traveler's Guide to the Stars without paying homage to Douglas Adams' Hitchhiker's Guide to the Galaxy, right? And the very first quote I put in the book is this: because the most daunting challenge of traveling to the stars reverberates from this one problem, and that is that space is really, really big, okay? And that is an understatement. This picture it gives an example of how big our local neighborhood is of nearby stars. You can see the nearest star system at over 3 light years away, which is the Centauri system, and then going outward to about 6 light years, what the potential destinations might be if we ever decide to send voyages, whether they be robotic or human, to explore other worlds. This is a very misleading chart. This makes you think these things are close to us and that it's relatively easy to get there. It's not. Think of these numbers. The speed of light, and you have to forgive me, I think in English units, being an American, so I think of how long it takes to get to the stars, and light traveling at these speeds takes over 3 years to get here. And I do want to mention, for those that don't think you'll ever touch the stars, if you go out at night and you look up at those twinkling lights in the sky, some of those are hundreds, if not thousands of light years away. Think about that photon that's been traveling through space for all of that time that falls on your eye. You are touching another star when you do that, okay? So the universe is touching your body physically when you look at the stars. I just gave myself goosebumps, okay, thinking about that. So you are actually touching something that emitted from a star perhaps before you were born, most likely before you were born. And if you look at numbers like that, you don't understand them. We understand numbers like this. I just flew in from the USA. It took me the better part of the day, thanks to connections and delayed flights, to get here. On the space station, they traverse around the Earth every 90 minutes. That's great. That's really fast. If you think about going to the moon, the distance there is comparable to what I've driven my car, which is a 2005 Honda. Over the last 15 plus years, I have approximately driven to the moon. And so I have an intuitive feel for what that distance is. When we start talking about interstellar distances, I would contend that even astronomers don't really understand the numbers because we don't experience them. We don't have them in our mindset. So let's give some examples to talk about that. And let's start in the solar system and create our own ruler, okay, to measure the distances to the stars that we have to traverse. The Earth to Sun distance is 1 astronomical unit. Great, 1 AU. What does that mean? In English, that means 93 million miles. In the year units that you're used to, 150 million kilometers. Do you understand what that distance is? No, you don't have any experiential basis for that. So I'm going to put it into a similar system that astronomers do. They use what's called the astronomical unit. I'm going to use 1 meter. Let's reduce this distance to something we experience every day. And that distance, which takes light 8 minutes to get here from the sun, is going to be 1 meter, okay? On that scale, the Neptune distance, the outer planet, is about 30 meters away. It's out in the yard, okay? Out in the front part of the building. It's not that far away. It takes us 10 years, on average, to send a spacecraft to that distance. 10 years to go that far. That's only 30 meters. If you want to get to the nearest star on LES's scale, you have to go to Ostrava in the Czech Republic, okay? And that's with the distance from the Earth to the sun being 1 meter and scaling it to kilometers. That's the nearest star. That's the challenge. So can we go? Well, the answer to that question is going to be after this, because we really want to go to these exoplanets, but remember, I'm a science fiction reader. What I'm worried about is this is where the most interesting place is, right? So when I talk about going to the stars, I don't just necessarily want to go to what's next door. I want to enable us to go anywhere, and are the laws of physics going to allow this? The answer to that question is yes, but you have to think differently, and you have to think on different scales that we normally think of when we talk about space exploration. We are already sending our first interstellar explorer, and that's the Voyager probes. They're on their way out of the solar system. They were launched in the 1970s. They're on their way. Unfortunately, even if they were pointed in the right direction, which they're not, to reach the nearest star system, the Proxima Centauri or the Alpha Centauri system, would take 70,000 years. I would contend that is not practical interstellar travel. I put together a unit in my own head of what is practical, and that practical distance for me is a trip that takes no more than 1,000 years. Now, Les, that's a long time. Why did you pick that? Because we are standing and sitting in a country and a culture that goes back well over 1,000 years, all right? So we have in our experiential base of living, and as descendants of the people who built the great cathedrals of Europe or the Great Wall of China, and all of the historic sites, the pyramids, civilizations that have lasted many thousands of years. So I picked that metric as the upper limit of what's really a practical interstellar voyage. Will rockets do it? The answer is emphatically not. Thanks to something called the rocket equation and the fact that you have to pack more fuel to go faster, which makes it harder to move your spacecraft because you added all that extra weight. To go a little faster, you have to add more fuel, which means you have more weight to move, and eventually it just becomes impossible. And chemical rockets, thanks to the release of energy in the chemical reactions in the engines, are really almost as high as the theoretical limit, which means chemical rockets will never get us to the stars. I've also worked on in my career something called electric propulsion, which is how you accelerate a spacecraft using electric and magnetic fields instead of chemical energy, which allows you to get higher performance out of your fuel. You get about 10 times the amount of thrust performance from an electric propulsion system per kilogram of fuel than you do with a rocket. But even those aren't efficient enough to get down to a practical time, which I would consider to be 1,000 years. You're still well over 10,000 years. Then I have colleagues, and I've worked on for a couple of years also in my career, nuclear propulsion, nuclear thermal propulsion, where basically you take a fission reactor, like we have generating power in many countries around the world, and you use that heat to accelerate your propellant to very high speeds to get high efficient rockets. You still can't do it. Trips would still take more than 10,000 years. So even releasing the energy of splitting the atom is not enough energy to get us to the stars. This is going to be difficult. How are we going to do this? Fortunately, there are some rockets, and I define a rocket as something that moves by throwing some kind of reaction mass overboard. Very simplistically, if I were crazy enough to be up here on a skateboard and throw a basketball this way, conservation of momentum would push me this way, and I would be a rocket. So what we need to do with a rocket is get a lot of energy in that exhaust so I get a lot of energy in my motion. So are there different types of rockets that can do that? The answer to that question is yes, there are. Let's begin with the next level of atomic energy, which is not fission propulsion, but fusion. Now recall, as I told you, to think about that photon that traveled all that distance through space to reach your eye. That was created through a fusion reaction in a star. And that's where it takes its mass and squeezes hydrogen atoms primarily together to the point where they fuse into helium. They release energy. That gives the outward pressure that keeps the star from collapsing on itself. It produces the heat and light that we experience here on the Earth. If you could tap that fusion energy to drive your propulsion system, the answer is yes. We could have a voyage of under 1,000 years for a robotic probe. And if we're really, really good at our technology, we could build something that might eventually take humans to that distance. The challenge is we have to get break-even fusion propulsion on the ground. We have to miniaturize it to the point where it will be in a spacecraft and be able to put it in that spacecraft to make it go to the stars. I'm not saying the engineering is within hand. As a physicist who works on teams at NASA where I come up with ideas for missions we go do and new technologies, my team hates it. I'll say, oh, you know, we ought to be able to do this. You guys figure out how to make it work. That comes with some interesting challenges. Some really revel in that challenges. Others look at me like I'm crazy, and of course I replace them on the team because I want people who have a can-do attitude, and we don't always succeed, and that's part of what we do in advanced technology development and as a technologist. So what else, Les? Well, I had the privilege of meeting this gentleman circled on the bottom right of this picture, Dr. Freeman Dyson, a few years ago. And back in the 1960s, he came up with a really crazy idea that might actually work. And that crazy idea was Project Orion. Project Orion, very, very politically incorrect. It basically is, imagine this. Imagine you get a submarine, they're sealed, you stand it on end, you put a big steel plate the size of this auditorium, but much wider, underneath it, and begin exploding small hydrogen bombs, one every 3 seconds, right underneath that plate. Boom, boom, boom. You rapidly get your spacecraft off the surface of the Earth, and you can load enough small nuclear devices in there to get up to a few percentage of the speed of light before you leave the solar system. Of course, you trash the Earth in the process. Details. But theoretically, this ought to work. It was exciting to meet Dr. Dyson. If I get a chance to talk to some of you later, I will tell you the benefits of sometimes breaking a rule to get someone to tell a story. If you're interested in learning more about this, there's a great YouTube video where they did non-nuclear testing of this back in the early 60s. It's silent because it was filmed on 8mm film before they all had the audio features included, but it's fun to watch. This idea, of course, was put on the shelf and never implemented and not seriously considered. And finally, I have for rockets, I have to pay a tribute to the show that really motivated me. And I see a lot of red shirts out here, and if you know Star Trek lore, that means you're the ones who are expendable when we go down to the planet and the monster will eat you. Sorry, we're going to lose you on a crew member. But this was an episode where they were putting what's called an antimatter bomb to destroy this alien. Well, antimatter is real. okay? Antimatter is produced at the CERN nuclear reactor facility. Imagine a proton, a nuclear accelerator facility, the CERN and other accelerators around the world. But it's really a different kind of matter. Think about a proton, which makes up an atom, or an electron, which circles it. Now imagine that you take this proton, which by definition has charge of +1, and you create something that looks just like a proton, but it has a negative charge. It's called an antiproton. And the electron, there's an antiparticle for it called a positron. And these positrons look just like an electron, but instead of a -1 charge, it has a +1 charge. There are other differences as well, but those are the ones we think of. And the interesting thing about matter and antimatter is when you put it in contact with each other, it goes through a process which is called annihilation. And that annihilation converts all of their mass directly into energy. And that energy is not all useful. A lot of it's gamma rays, X-rays, secondary particles that come out, but it is a very efficient battery. It is the best battery we can possibly have because it goes all the way to Einstein's famous equation, E = mc². And that equation tells you that if you have a little bit of antimatter and a little bit of matter, you get a lot of energy released. Just to give you an example, if I had a teaspoon of antiprotons and dumped them on the floor to interact with the protons in this room, it would be in the end of this city, and there would be a major, big, large, smoking hole in the ground where this city and university used to be. That's the kind of energy contained in antimatter. It's produced in nanograms per year. The amount that is produced is not dangerous because it interacts a few fractions of atoms, of a mole at a time if you're a chemist. Very, very small amount. It's contained in magnetic fields. We just don't know how to make it in the quantities we need to go to the stars. However, if you eat bananas and you have a banana in your home, there is a radioactive decay process going on in that banana, thanks to the ground it was grown in, where there's a particle of antimatter produced about every 70 minutes that quickly annihilates in the banana and poses no health risk to you, but you are producing antimatter. So this is one of those fun facts to take home to your family, is when there's a bunch of bananas on the table, you have your own antimatter factory right there in your home. Now, if we could find a way to tap into this on the banana plantations, maybe we would have our propulsion ship to go to the stars. The problem is, we don't just need a few atoms of antimatter or a teaspoonful of antimatter. We need 1,000 tons of antimatter. That's a lot of antimatter. Is it possible? Yes. Do we know how to engineer it and store it and put it on our spacecraft? Not yet. Go ahead, students. That's your homework, right? Do that before the end of my journey through this life. Okay, is there another way? Yes. That way is off-board energy through something called a sail, a solar sail. Now, real quickly, this is something that in my day job I've spent a lot of time working on. It's available in the public literature. A solar sail does not use any kind of rocket. Its energy source is offline. So this light, this big bright spotlight that's shining on me, or the sun that we'll see this afternoon and tomorrow as we look at the Rover Challenge course, is putting out light, little particles of light called photons. These photons have no rest mass, but they do have momentum. So as that light reflects from me, it's pushing on me. I don't feel it because it's an extremely small push. You would never feel it on the Earth. In fact, it's so small it's almost impossible to measure here on the Earth. But when you get into space, and you unfurl a large, lightweight reflective sheet that looks like aluminum foil, but is much lighter in weight, and the sun reflects from it, just like the wind reflects from a sailboat, that sail will move. And if a spacecraft is attached to it, it'll drag the spacecraft with it. And this type of propulsion is very, very nice, because for small spacecraft currently, you can build sails large enough to get an acceleration to get them up to very high delta V, very high speed, and very high propulsion performance, so that as you're close to the sun, you can go to destinations that rockets can't take you because they run out of fuel trying to get you there or to station keep in those locations. And the reason for that is because the sunlight is constant. It's never nighttime in space unless you're in the shadow of a planet. So you have this constant acceleration pushing on your sail, which enables you to go to places which you otherwise could not have gone. Solar sails have flown in Earth orbit. I was the principal investigator for a sail that launched on Artemis 1. It was called Near-Earth Asteroid Scout. Unfortunately, that demo did not take place because the spacecraft never called home. We were unable to deploy the sail, but you can learn about what the mission would have been, all the work we'd put into building its 86 square meter sail on the internet. And there's another mission that might happen as early as 2028 that NASA's working on, and it's called Solar Cruiser. And this will be a 1,600 square meter sail, 2.5 microns thick, that would deploy from a small spacecraft and go towards the Sun-Earth L1 to demonstrate its operation. So, this is my ambitious plan. My ambitious plan for off-board energy, which is just as challenging as my onboard antimatter or fusion drive, but it's physically possible, is to build sails that aren't 1,600 square meters, they're square kilometers. And instead of deploying them at Earth orbit, we deploy them close to the sun, where the sunlight pressure is very, very high. These sails would then get enough acceleration as they leave the solar system to get our voyage to the stars in less than 1,000 years. And if you use off-board energy, like a laser, to shine on that sail, you can get it to go faster. So there are different groups that are researching this. One I'm most familiar with is the Breakthrough Starshot. It's a privately funded group to build laser sailcraft to go to Alpha Centauri. They are working on the technologies now, and I wish them great success in what they're doing. But this idea is not new. It's been around for a long time. What's new is the technologies of lasers and lightweight components have caught up and might make it actually feasible. So, I really want to talk about some of the practical aspects right now. Let's assume we have a fantastic engineering team that instead of building a rover next year, they build my antimatter system or my laser-driven solar sail, and we're going to do a test. And we want to send that to the nearest star, a small spacecraft, something reasonably sized that might be able to send data back. So let's assume that something a kilogram in mass, with whatever the propulsion system is, and that kilogram of mass is roughly equivalent to a pineapple. So if you've been to the store and held a pineapple, you're holding the size of the spacecraft. Let's launch it, and let's assume we do it with 100% efficiency. So we get up to 10% the speed of light. This is the energy equivalent contained in the kinetic energy of motion of that satellite. It's traveling to the stars at 10% the speed of light. And if we miss the flyby of the planet to take pictures, and instead we hit a planet around Alpha Centauri, we would hit with an energy equivalent of 7 Hiroshima atomic bombs. And we would have just started our first interstellar war. So we want to make sure that if we send a robotic probe to the stars that's not going to slow down and is just going to fly by and produce science, that what we do with that spacecraft is we don't hit the planet, okay? That would not be a bad day for any relations with people or creatures or whatever might be on that world. Lastly, before I get to the questions and answers, I address this in the book because I'm asked this question a lot. Les, are you talking about abandoning Earth? My answer to you is absolutely not. We live in what is perhaps, for our form of life, a unique or nearly unique, wonderful place to live. We are adapted to live here. I think we ought to be using space technology and resources to help save our planet so that we can have our ducks in a row to expand into the solar system and eventually go to the stars. And I contend that there is a very high moral value here. I would contend that in this, what looks like largely empty universe, largely devoid of life, we haven't found other life on other worlds, and if we do, it's going to be rare and in niche places. Most worlds are dead and will never have life. Life is good, okay? I contend that preserving life is a positive moral value, and I mean that from the amoeba to the human. All forms of life are worth preserving, except a few viruses that we all know and don't like very well right now in our culture, right, in our world. However, I can argue that the love that I feel for my children, the enjoyment you get out of seeing art, great films, reading good books, that is a high moral value, and that is good, and that is worth preserving. And because the Earth is a fragile place, all you have to do is look at geologic history. This really was driven home to me when I first read about something that happened many tens of millions of years ago called the Permian extinction. The Permian extinction was apparently caused by massive volcano eruptions in modern-day Russia. These volcanoes put so much soot into the upper atmosphere that photosynthesis stopped. The oceans became acidic, and 90% of all the species on Earth ceased to exist. Then we had the KT impact, which ended the dinosaurs, which a lot of space enthusiasts are familiar with because we believe it was caused by an asteroid impact. Life on Earth is precious and fragile, and we need to make sure that this moral good, which is life, is spread throughout the universe. Now, the other question is, Les, this sounds like colonialism, imperialism. Are you going to repeat the histories of the past? My answer to that is I sincerely hope not. And that's why I look back to that visionary program, Star Trek, because I think that should guide our exploration of the universe. They had what was called the Prime Directive, where they would not interfere with other cultures if they found them. I think we ought to extend that to be, even if we find microbial life, that's the province of science, not human settlement. We need to be finding worlds that are dead, that otherwise would not have life, and undertake the thousands of year process to terraform them, to make them adaptable to our life. Now, these are all different thoughts that I have written into that book, but I also write science fiction, where I'm able to explore some of this and what it means to be a person or a human in this fantastical future that's trying to actually accomplish some of these tasks and the challenges you'll face. So if you're interested in my work and want to transition from the popular science nonfiction, I also write science fiction where I actually can delve into the whatever the engineering is, here are the challenges we have to face at the end. So to conclude this presentation and get ready for the panel discussion, and I hope we have good time for question and answer, is the universe is full of potential. It's full of planets. There's a lot out there to go see. Physics says we can do this, not just from a propulsion point of view, but from power, from the fundamental aspects of human life support. There are breakthroughs in biology, synthetic biology, genetic engineering that might enable us to store people or to take us and go to the stars. We just don't have the engineering side of the biology intact yet. The life support systems that we're developing for the space station, for exploration of Mars, are getting very efficient. Perhaps these can be adapted to keep people alive for long journeys to the stars. So within the laws of nature that we have today, it looks like this is something we crazy humans on this third planet from our star might be able to do. And I would contend we need to start thinking about it, getting the world to think in a positive way so that maybe that'll spin off and make more people more positive about protecting our planet today so that we can have that Star Trek-like future that we want to have. So the question is, can we get here? Can we get to the Centauri system and look back toward that one star in the sky, which is our star, the sun? Okay? The answer is, I think we can. Lastly, I have to give this quick story. I was asked in a management class, one of those things you have to go through when you work in a big organization, what do you want to have as your professional legacy? I would like my professional legacy to be a footnote when the history of the first settlement on a planet around another star is written. And they have this 1,500-page book about what it took to get there. I would like for my work to be an endnote or a footnote in that book. That's my career goal. I will never see that, but posthumously, that's what I'd like to see happen. There is a group that thinks about this. It's called the Interstellar Research Group. I'm a founding member. We've had 8 meetings. Our last one was in McGill University in Canada. Our next one will be in 2 years in Texas at Texas A&M. This is at Interstellar Research Group, irg.space. I encourage you to look into that if you want to find other forward-thinking people who look at the challenges of ultra-deep space exploration. It's a nonprofit group. They do give some scholarships for the students that are out there. It's definitely worth looking into. And last is the blatant commercial message for my books and what I write and talk about and what has enabled me to be here today, which is talk about my latest book, A Traveler's Guide to the Stars from Princeton Press. Came out about a year ago. But I would encourage you, I don't just need people to buy the book or whatever, write to me. I love hearing from people who've heard my lectures. I've been getting a lot of email as a result of some of the lectures I've given recently. I'm not the fastest person to respond, but I always respond. I will not ignore you. So if you have questions, would like to reach out, share your thoughts, get involved with any of these activities, please feel free to do that. I'd love to hear from you. Thank you very much.
Thank you very much, Les, for your inspiring talk and a lot of interesting things that we learned. Actually, I'm an astronomer. Just a moment, and I just look at the book cover of your of the book that you just mentioned. I think these constellations are faked, aren't they?